Welcome to the next lecture of topology, separation axioms. So till now we have done some theory, some theorems, some lemmas, some equations about T0 spaces, T1 spaces, T2 spaces and regular spaces and T3 spaces. Now we are moving towards the normal spaces. So there is a little bit theory that is to be understood definitely. Why T4, why normal, and why there is a space known as T3 and half. So first of all there is T0, then T1, then T2, then there is regular spaces, and if a space is regular as well as T1, then it is T3, and then there is normal space which we are going to study today. And if a space is normal plus T1, then it is T4 space, but there is a space in between these two, so there is a gap. So there is a space completely regular, and if a space is completely regular and T1, then it is called T3 and half. The question is why it is named as T3 and half. Why not T5? Why not T6? Why T3 and half? So the reason behind this is that first T0 was discovered, then T1 was discovered, T2 was discovered, T3 was discovered. After T3, T4 was discovered, and T3 and half was discovered after long time. The question arises why it is put in between these two. That is because every T1 space is T0, every T2 space is T1, every T3 space is T2. Similarly, every T3 and half space is T3, and every T4 space is T3 and half. So it possesses a property, so why it is placed in between T3 and T4. But today's lecture we will concentrate on normal spaces and we will concentrate on T4 spaces. So I am going to start with the definition of normal spaces, and then we will move on to T4 spaces, and then some properties of normal spaces and T4 spaces. So first of all, definition of a normal space. What a normal space is. First of all, I like to illustrate this diagrammatically. So here is your space X with some topology tau defined on it. This topological space will be called normal if for any two disjoint closed sets. So it is a closed set, you can say F1. Here is another closed set, you can say F2. And these two are disjoint. For any two disjoint closed sets F1 and F2, if you can find two disjoint open sets now, if you can find two disjoint open sets, suppose G1 and G2, disjoint open sets G1 and G2 such that G1 contains F1 and G2 contains F2, then it will be a normal space. F1 is contained in G1, F2 is contained in G2, and one thing is clear, that G1 intersection G2 is phi. Why? Because G1 and G2 are disjoint open sets. So if for any two closed sets F1 and F2, you are able to find two disjoint open sets G1 and G2 containing them, the space will become normal. And now I'll write this definition analytically here. It was diagrammatically, and now we will move on to the analytical definition. Let X tau be a topological space, then X tau will be called normal space if and only if for every pair of disjoint closed sets F1 and F2, we can find a pair of disjoint open sets G1 and G2 such that F1 is contained in G1 and F2 is contained in G2. If this axiom is satisfied, then we say that the topological space is normal. This axiom is known as Unison's axiom. This is known as Unison's axiom. So this is an axiom given by Unison that for any two closed disjoint sets F1 and F2, there exist two open disjoint sets G1 and G2 containing them, then the space will be called normal. Just before giving this definition, I have told you that if a space is normal as well as T1, then it is T4 space, then it is called T4 space. So one thing comes to mind, can there be a space which is normal but not T1? Because normal and T1 will give you the T4 space. So definitely there will be spaces which are normal but not T1. So I am giving you an example of a space which is normal but not T1. So let X be your set containing three elements A, B and C. Now consider the topology tau having four sets phi, singleton set A, the set containing 2 points B and C, and the whole set X. Now this is a topology. Why? Because all the four axioms of topology are satisfied by this set. So this is a topology. So X along with this topology, tau is a topological space, and now we will show that this is a normal space, but it is not T1. So how to check it is normal or not? For normal spaces from where we are to start, we will have to take a pair of disjoint closed sets and we will try to find a pair of disjoint open sets containing them. If we are able to find these two sets, then the space will be normal, otherwise it will be not. But it should be true for every pair of disjoint closed sets. So what the closed sets here are. So phi is open, that means X is closed. Singleton set A is open, so that means the set containing the points B and C is closed. Now the set containing B and C is open, so its complement, the singleton set A is closed. X is open, so its complement phi is closed. Now I need two disjoint closed sets. There are several possibilities. What these possibilities are? First of all, you can have pair as phi and singleton set A. They are closed both and are disjoint. Their intersection is phi. You can have the pair as phi and the set containing the elements B and C. It is also a pair of disjoint closed sets. You can have phi and X. You can have the set A and the set BC. And there are no more choices. These are the only choices. You cannot have more choices for having pair of disjoint closed sets from this topology. Now in all these four cases, we will have to find a pair of disjoint open sets containing them. So in the first case, this is your F1, this is your F2. Take phi as your G1 also and singleton set as your A as your G2 also. Why? Because this phi is closed, but this phi is also open. This singleton set A is closed, but this singleton set A is open also. So if you are considering them as closed sets looking here, you can consider these two as open sets looking here. So these are the two disjoint open sets, G1 containing F1 and G2 containing F2. So in the first case, the Unison's axiom is okay. But I told you earlier that it should be satisfied for every pair of disjoint closed sets. So we will have to still check these three more pair of disjoint closed sets. For the second one, this is your F1, this is your F2. The first case is okay. Now we are moving on to the second one. Once again, phi is your G1 and take BC as your G2, and once again you are able to find a pair of disjoint open sets containing a pair of disjoint closed sets. So the Unison's axiom is satisfied once again. In the third case, again, if your F1 and F2 are phi and x, you can take G1 and G2 also as your phi and x. These are disjoint open sets containing the disjoint closed sets F1 and F2. And similarly here, this is your F1, this is your F2. So you can have here G1 as singleton set A and G2 as the set containing B and C. So these are the two disjoint open sets containing the disjoint closed sets F1 and F2. So the Unison's axiom is once again satisfied here. So in all these cases, whatever were possible, in every possible case of pair of disjoint closed sets, you are able to find a pair of disjoint open sets containing them. That means Unison's axiom is completely satisfied. That means your space is normal. But is it T1 also? You know that a space is T1 if whatever 2 points you take from the space, whatever the 2 points you take, suppose I am taking B and C, two distinct points B and C. Now what I want, to make this space T1, I need two open sets, one containing B and not containing C, and one open set containing C and not containing B. Is it possible? Here. So I am rubbing these four closed sets from here, and I am talking about the four open sets now. If we take phi, then phi neither contains this nor contains this. So phi cannot be an open set containing one of them and not the other. Similarly, this set cannot not work again, because it does not contain either of these two elements. If you take BC, then okay, it contains B, but it also contains C. So you cannot have the set BC here. It will again be a problem, because you want open set containing B and not containing C. And similarly, you need an open set containing C and not containing B, which is again not possible here. And if you move on to the fourth set X, the similar problem is once again there, because if X contains B, then X also contains C. If X contains C, then X also contains B. That means you are not having open sets G1 and G2 such that B belongs to G1 and C does not belong to G1, and C belongs to G2 and B does not belong to G1. So there are it is not possible to find two open sets such that each one of them contains one of the elements and not the other. So this space is not T1. This is normal but not T1. And if a space is normal as well as T1, then it is called T4 space. And now we will move on to the first theorem on normal spaces. So write down the statement of the theorem. So first I am writing the statement and then I will move on to the proof. Let X top be a normal space. Let X top be a normal space. Then X top is normal. X top is normal if and only if for every closed set F and for every open set G containing F, open set G such that F is contained in G, there exists an open set H satisfying F is contained in H and H is contained in H bar and H bar is contained in G. So if you are having an open set H satisfying this condition, then the space is normal, and vice versa, because you are having if and only if here. If and only if means we will have to prove it directly, and we will have to prove the converse part of the theorem also. So I am going to prove the state part first, and then I will move on to the converse of this theorem. So let us start with the proof. So first, for the direct part, I suppose that the space X tau be normal. Let X tau be normal space. Also, I'll take one closed set F and an open set G that contains F. Let F be closed and G be open such that F is contained in G. Now, you require an open set H such that F is contained in H and H is a subset of G. Now you require that. So F is a subset of G. This directly means that F intersection with G complement is 5. Because you know that if A intersection B is, if A is a subset of B, then A intersection with B complement is 5. That is a well-known result from basic set theory. So that I have applied there. So if F is a subset of G, then F intersection with G complement is 5. Now F is closed. G was open, so G complement is also closed. So you are having a pair of disjoint closed sets, F and G complement. F and G complement is a pair of disjoint closed sets, but the space is normal. So therefore, by the Unison's axiom, there must exist a pair of disjoint open sets containing them. So therefore, there exists a pair of disjoint open sets, say H and V, such that your F is contained in H and your G complement is contained in V. What you require to prove? You require to prove that there is an open set H satisfying this condition. Now F is a subset of H that I have obtained for the open set H. H is open set and F is a subset of H. So this part is okay. Now H is a subset of H bar is always true. Why? Because every set is a subset of its closure. So H is a subset of H bar is also true. Now we are to concentrate on this part that H bar is also a subset of G. That is only required to be proved. That will show from this result. Since H and V are disjoint, therefore H intersection V is 5. Now look that H intersection B is 5. G complement is a subset of B. So G complement is a subset of B directly implies that V complement is a subset of G. Because from the basic set theory, if A is a subset of B complement, then B is also subset of A complement. It is basic set theory. So I have applied it here. V complement is a subset of G. Now H intersection B is 5. Once again, from your basic set theory, you know that if A intersection B is 5, then A is a subset of B complement and B is a subset of A complement. So H intersection B is 5 means H is a subset of V complement. H is a subset of V complement. Also, we know that if A is a subset of B, then A bar is a subset of V bar. That is also a well-known result from your previous knowledge of topology. So this result I am going to use here. Here, H is a subset of B complement. That means H bar is a subset of V complement bar. Now, move on to the next part. Your V is open set. So what about V complement? V complement is closed. And closure of a closed set is the set itself from our previous knowledge. So V complement closure is same as V complement. Now, H bar is a subset of B complement and B complement is a subset of G. From these two, you can directly say that your H bar is a subset of G. Your H bar is a subset of G. I have told you that H is always a subset of H bar. Now look into these three. This one, this two, and this three. Your F is a subset of H. Your H is a subset of H bar. And your H bar is a subset of G. And what about H? H is an open set. So you have obtained an open set H such that F is a subset of H, H is a subset of H bar, and H bar is a subset of G. That means we have proved the required result that was given in the statement of the theorem. Now we will prove it conversely, because the theorem contains the part if and only if. So converse part also need to be proved. For the converse part, we will suppose that the given hypothesis is satisfied. That means for every closed set F and for every open set G containing F, there always exists an open set H satisfying F is a subset of H is a subset of H bar is a subset of G. That is given to us. Now we will have to prove that the space is normal. Since we have to prove that the space is normal, from where we will have to start? We will start by taking a pair of disjoint closed sets, and we will try to find a pair of disjoint open sets containing them. So let us start with, let F1 and F2 be two disjoint closed sets. So I have started with two disjoint closed sets. Now I will try to find two disjoint open sets, one containing this and other containing this. F1 and F2 are disjoint. So that means their intersection is phi. And if their intersection is phi, I have told you, if A intersection B is phi, then A is a subset of B complement and B is a subset of A complement. So once again here, F1 intersection F2 is phi. This means your F1 is a subset of F2 complement. F1 intersection F2 is phi. That means F1 is a subset of F2 complement. That means now F1 is closed and F2 is closed means F2 complement is open. So a closed set subset of an open set. By given hypothesis, there exists an open set H. There exists an open set H such that F1 is a subset of H, is a subset of H bar, is a subset of F2 complement. Now F1 is a subset of H. Now I'll concentrate on the second part, that H bar is a subset of F2 complement. From here you can have F2 is a subset of H bar complement. F2 is a subset of H bar complement. H bar is a closed set, so its complement is open. F1 is contained in an open set. F2 is also contained in an open set. Now only thing remains to prove that their intersection is phi. That means these two open sets are disjoint. So I am taking, suppose that this intersection of these two is not phi. Suppose, if possible, H intersection H bar complement is not phi. Suppose. So if it is not phi, there must exist some element P belonging to H intersection H bar complement. So this means P belongs to H and P belongs to H bar complement. P belongs to H bar complement means P does not belong to H bar. And H is a subset of H bar. So if P is not in H bar, how P can be in H? So P does not belong to H. P belongs to H and P does not belong to H is a contradiction. And this is the contradiction because we have supposed that their intersection is not phi. That means these two open sets are disjoint. So we have obtained a pair of disjoint open sets, one containing F1 and other containing F2. That means our space is normal. So I am going to stop this video here. In the next video, we will do more and more theorems on normal spaces and T4 spaces. Thank you once again.